All right, we are in problem 5.2, lesson 5.2, problem 2, page 308. We've just noticed that downtown is decreasing in population and uptown increasing. They're both exponential functions. Sorry, forgot to start that crew. Now, we're going to use our graphing calculator to look at what does this look like in terms of a graph. They're giving us some bounds here. When they give you the negative 100, positive 100 by 0 and 30,000, those are the x and y boundaries that they want on the graph. That's what you're going to have to put onto the window of your calculator. So go ahead, open up calculators, turn them on. Go to window. This minus 100, that's the x-min, negative 100. Sam, do you have a calculator back there? I've got one right here. It'd be good for you to follow this. Okay? And then that positive 100, that's the x-max. It doesn't tell us what to do with a scale, but if I'm going from negative 100 to positive 100, how about we go by fives? Excuse me. We need a reasonable scale. Now, in the y values, it's going from 0 to 30,000. The negative 100 to positive 100, that's a range of years. 100 years ago and 100 years ahead. But this is population from 0 to 30,000. So y-min 0 and y-max 30,000. 3 with 4 zeros. And then if I'm going all the way up to 30,000, I bet you a good scale is 100s. They don't tell us what to do for scale. I guess the calculator would figure it out, but we can think in our head about that little tiny graph. How many lines would you have to put into the little tiny graph? Okay, so let's analyze the the y-intercepts of each function. Identify the y-intercepts. I think we're going to need to graph them right now to find a y-intercept. Well, actually, let's think about this. If I'm going to have a y-intercept for a function like this, it's going to be at t0, time 0. What happens, do you guys remember, if I take a function like for downtown, 20,000, 1 minus 0.015, and I put a 0 right here? Jerry? It equals 1. So everything in this parenthesis, which is what's raised to a 0, equals 1. So the y-intercept for downtown is 20,000. What's going to be the y-intercept for uptown? Do we even need to do the math? Take a look at the function. What part of this function disappeared or turned into 1 for downtown? Again, the intercept's going to be when t is 0. So the whole parenthesis piece is going to turn into 1 when t is 0, right? I don't know if you're agreeing there. So let's write it out. 6,000 times 1 plus 0.018 raised to the 0. Anytime you raise anything to the 0, that equals 1. So this is 6,000 times 1, or 6,000. What what does 20,000 and 6,000 represent for downtown and uptown? Population at time 0, which is current time. It's not back a couple years. It's not forward a couple years. Time 0 is right in the moment. I have it. No time has elapsed, and I'm not thinking backwards. So the y-intercepts are current populations. Describe how you can determine the y-intercept of each function using just the formula for the population. I wonder if we were supposed to be looking at the graphs there to do that, because we just used the formula. What did we do in that formula to figure out the intercepts? We replaced something with 0. Replace t with 0. Let's go ahead and look at graphs of our functions. We were supposed to do that up there in number 1. We got to put them into y1, and I have some old stuff I need to clear out. Okay, for the first y1, I'm going to put downtown. Population is 20,000. Oops, that's going into y2. Y1, 20,000, 1 with 4 zeros, parentheses 1 minus 0.015, close the parenthesis. And then to make the t an exponent, I use this little caret button, which is underneath clear. And then that exponent's going to be a variable, so xt theta n is what I push. Then I go down to y2. And now I'm going to do uptown. This one starts with 6,000, parentheses, 1 plus 0.018, close the parentheses, caret button, x. Are you with me to there? Again, one of the tricky parts is you had to put stuff in parentheses, and then you had to remember to make your variable an exponent. Let's see what happens when we graph. Okay, that's one going down. That must be downtown. And very slowly, that's one going up. That's uptown. Let me see how our people over there at TES are doing. How'd your graphs turn out, guys? You got it, Isabella? Is that a thumbs up? Good. Okay. A lot of times the window's the hardest part, and they gave us window. Oh, somebody's off to the side that we can't see, but their thumb is happy. Excellent. Okay, and again, too, are these graphs linear?
No.
No.
Exponential.
They're exponential, and that means they do this either gradual and then swoop, or down and then level off. Okay, there's a part of their graph that moves steeply, and then there's a part of a graph that's like smooth. All right. Moving along. Number 3. Use a graphing calculator to answer each question. Describe your strategy. How long will it take downtown's population to be half of what it is now? Half of what it is now. So this is downtown, and its population now is 20,000. What's half of that?
10,000.
Half will be 10,000. So what are kinds of things we can do on our calculator to find the years where it turns into 10,000?
Intersect.
Intersect. All right, beautiful. So let's go to y equals. And I think we can leave both in. I bet you we'll have to figure out how to get the right curve when it asked us to guess. So, but let's go down to y3. And we're going to put in 10,000. That's the y. Whoops, I went too far. Back it up. Delete. So 10,000 has 4 zeros. Okay. I'm going to go to second calc, because I know from what we were doing yesterday, that's where intersect is. And you guys see intersect? Cursor your way on down to 5. Enter.
It's gonna be funny.
Excuse me?
It looks funny. Looks like a jungle gym.
Jungle gym. Okay, it's looking nice. So first curve, do you see where the cursor is? That's good. That's on the downtown curve. So I'm going to put yes. Second curve, though, it pops on down. I wonder how I get it to the other line, because now I need that cursor on the straight line. I'm going to try this. That jumped up to there. This jumps down to there. So maybe backwards? No, forwards. Second curve. No, how do I get it onto the line? I wonder if I have to go back out and get rid of my downtown. Or, do you see how I've moved my blinky little cursor? Okay, I've got it on the intersect, but that's the wrong intersect, huh? Move it farther, move it farther. No, oh, this is what I need to do. Let's go back. And, nope, nope, nope. All right. I think I'm going to have to take, I'm sure there's a way to do this with both in there, but since we're only interested in downtown, I think I might have to take uptown out. Okay, so let's, I went back to y equals, I'm going to clear out uptown. I'm going to put the 10,000 in as y2, and then clear out the y3. That way, I know how to do intersect when there's only 2 things in there. Second calc, 5. There's downtown, I know because it's going down. There's the 10,000 flat line. And now it says first curve and it's blinking on the downtown. Enter. Second curve, now it's blinking on the straight line. Enter. Yes. Enter. All right. I have something that says intersection. It gives me an X and a Y, and I can see that the blinky cursor is right there in the middle. I had to do it by limiting my picture to only look at the 2 graphs, though. We know that the Y is 10,000. We told it that. Brian, what does it say for an X?
25.86.
That's a lot of years, huh? Well, maybe not in the age of a town, but downtown will get to half in 45 point, we'll call it 9 years. So just under 46 years. Okay, now we're going to do the same thing for uptown. I'm going to walk around and see if you can figure out how to put that into the calculator. Uptown's formula is up at the top of the page. You're going to have to load it into Y1 and then work the intersect feature.